The next problem, problem C, is going to bring us to the piecewise functions, okay? And piecewise functions we have to consider a little bit differently when we're talking about some of these things. The first issue that we're going to look at is the domain. So in looking at this function, the first thing for the domain that I'm going to look at is I'm going to look at what the two type of functions represent. Well, so what the two pieces represent. This first piece of the function, that's the equation of a line. So that's going to represent a line. I know that lines in general are continuous everywhere. So this piece by itself should be continuous. The second piece is a parabola, okay? Parabolas by themselves are also continuous. So these individual pieces are continuous. So now I just have to make sure that all of the points, including this one, are represented as actual points. Now, I don't need to see if the two pieces actually meet. Like, they can come in like this, as long as one of them has a closed dot and one of them doesn't, then we should be okay. So taking a look at this one's x is greater than 2, so this is where it comes in from the right, but it has an open circle. And this is where it comes in from the left because it's less than, but it's got the or equal to sign, so this circle is closed. So this circle is the point at 2, this circle is not the point at 2, so the domain is negative infinity to infinity. The domain is all real numbers because there's not a point where it doesn't exist, okay? End behavior, we're gonna have to determine end behavior for each individual function. So this is the end that's going to the right. So I'm gonna write this in limit notation just so that it's easier to see. End behavior. Okay, so if I do the limit as x goes to infinity of h of x, okay, and this is as x is going to the right, well, as x is going to the right, this line, because it has a positive coefficient, is going up. So this is going to infinity, okay? And as the function, as x goes to negative infinity, or as the function is going to the left, it's on this piece of the function. Well, this piece of the function is a positive parabola, and positive parabolas look like this. So as this function goes to the left, I'm not sure if you can see that. Let me draw that a little darker. Positive parabolas go like that. So as this function goes to the left, it's going to positive infinity also. So both ends of the function should be going to positive infinity. The x-intercept of the function, we have to consider two things. We have to consider where the x-intercepts of the line would be and where the x-intercepts of the parabola would be. Well, the x-intercepts of the line occur where the function equals 0. So let's solve that out. So 3x should equal 1, so x should equal 1/3. So this line hits 0, has an x-intercept at 1/3. But this line is only a piece of the function where x is greater than 2. X is 1/3 is not greater than 2, so this piece of the function is not going to hit the x-axis, okay? Because it stops at 2 and it doesn't hit until 1/3. We're going to do the same thing with the other one. 2x squared equals 0. So x squared, if I divide by 2, should equal 0. Square root both sides, so x is 0. Looking at this piece of the function, this is the piece of the function wherever x is less than 2. 0 is less than 2, so this is my x-intercept. 1/3 is not, because it's not that piece of the function. It doesn't fit the boundary that the function was given, okay? Y-intercept. Y-intercepts happen when we plug 0 in for x. So 0, if I plug it in for x, is not on this arm of the function because this is only x values greater than 2. So I'm going to use this one because it's 0 fits into this piece of the function. So if I plug 0 in for x, I get 0. So the y-intercept is y equals 0. Okay? Symmetry. Well, hopefully just by looking at this equation graphs as a line, this equation graphs as a parabola, so I'm going to have a section of the parabola attached to some sort of line like that, so hopefully you can just tell automatically that there is no symmetry in this function. But if you went through our test, if I changed the sign of this x, it would change this piece but not this piece, so that's neither. And this piece is even, but because it deals with this and it's piecewise, it is not symmetric. Okay, most piecewise are not symmetric. And then all discontinuities. Well, the discontinuity would exist at 2 if there was one. So let's see what they are. So discontinuities Let's see what they end up being. So as I go in from the left, so I'm going to do this in terms of limits again. So the limit as x goes to, and we're going to use our boundary point, as x goes to 2 from the right of the function. The limit as x goes to 2 from the right is this piece. So that's 3 times 2 minus 1. So 6 minus 1 is 5. Okay. Then the limit as x goes to 2 from the left of the function is the left arm of the function. So if I plug in 2 here, 2 squared is 4 times 2 is 8. So the right arm of the function comes into 5. The left arm of the function comes into 8. So this tells me that this function is coming in from the right to 5, and this piece of the function is coming into 8. So that's one of those situations where we have a jump discontinuity. So non-removable jump discontinuity at x equals 2. Okay, so that's what that looks like. And now we need to graph this. You can see, there we go. So this is graph C. Okay, so looking at graph C, I know that from 2, I'm approaching 5. So 1, 2, 3, 4, 5 from the right. And that is the open circle. Okay, and this graph, 3x minus 1, is a line that's going up. So it looks something like that. The graph of the parabola approaches 8. So 1, 2, 3, 4, 5, 6, 7, 8. It is closed in because of the or equal to part. And it is a parabola with an x and y intercept at 0, 0. So it looks, draw it parabola-esque. Curve that a little bit more. So it looks something like that.